All right, let's get started. Let me welcome you to today's lecture, Topics in Reinforcement Learning. And up until this point, we have mainly focused on online play algorithms, in particular approximation in value space and variants of rollout, its application to stochastic problems, deterministic problems, and so on. And we also talked about a few applications and case studies. This lecture, we're going to shift gear and start to talk about offline training algorithms, which is also an important component in our essential architecture, as well as some other parametric architectures. Here's the outline of today's lecture. First, we're going to give a short review of what we have done up until now, and also talking about our plan for the remaining lectures. Then we're going to talk about parametric approximation architectures for offline training. And this mainly includes some classical architecture like piecewise linear function and feature-based linear architecture, as well as neural network. Then we're going to talking about how to train those architectures. And after that, we're going to take a break. And then after the break, we're going to talk about more generally some incremental optimization methods for optimizing a large amount of sum of differentiable functions. And within that context, you can see the training of architectures would be a special case where all those differentiable functions are the functions of this parametric architecture. And after that, we're going to talk a little bit about neural networks and connect them with the previous incremental optimization algorithms. We're going to also cover or talk briefly about some key innovations that enable the training or the use of deep neural network. All right, let's get started. Here is the essential of the key architectures that we have go back again and again. And this is the Alpha 0 or MPC architecture, which is our starting point. It is composed of two essential elements, which we refer to as offline training and online play. And they can be designed or implemented to a large extent independently. And there is a lot of flexibility to modify this architecture by including some additional ingredients or remove some of the components and so on and so forth. So there are some key or essential difference between the offline training and online play component. To start with, offline training is done, as the name suggests, offline. And the goal is to train or obtain some terminal cost approximation or policy, some policy that we have access to. And it is done with the goal to approximate sufficiently well for almost all, if not all, states. So when training, we try to cover as many as possible the states. So we would like to have terminal cost or a policy that approximate well in a lot of states, at least the states that we anticipate we're gonna visit in our real-time operation. On the other hand, online play part, this operation is only done for states that we actually encounter in real-time operation. So this is one of the key difference. And the other difference, which is conceptually, the online play part is more important. And there is a subtle difference between the first step and future steps. So in this figure, it's the online play part involve 2 steps to look ahead. And starting from all the leaves of this look ahead tree, we run rollout with the base policy supplied by offline training that give us this policy network up to certain depths. And then the additional cost is supplemented by using the terminal cost approximation, which is given by a value network. And in this, the whole process need to be done in real time online. And the first step is conceptually the Newton step for solving Bellman's equation. Here I have a question. So if we look at this online play, multi-step look at minimization part, basically we're going to minimize over UK and UK plus 1, all the combinations of UK and UK plus 1 starting from xk. So if we look at this minimization formula, minimize UK and UK plus 1. Why is it different that UK? What makes UK different from UK plus 1? Conceptually, the first step is Newton's method, and the second step is not. So why those two are different?
Because no matter how many steps you have in the look ahead, you only choose the first action.
That's absolutely correct. So the difference is you actually use UK that you selected during this minimization operation, and you throw away all the future steps in this multi-step look ahead. So this is where it makes the difference. Okay, so in the first four lectures, we start with an overview and kind of big picture lectures, which is chapter 1 of the textbook. We set forth this offline training and online play, Newton step interpretation framework, conceptual framework. And after that, we cover some exact dynamic programming content that applies to deterministic, stochastic, finite, and infinite horizon problems. The goal is not really to cover, to a large extent, extensive theory about those topics. It's more about set the stage for you to understand the approximate method that we cover later on. And also in this stage, you already seen that, for example, this traveling salesman problem that in your exercise, it really make little sense to solve it using dynamic programming to get the exact solution, but it makes a lot more sense when you want to solve it approximately using rollout or approximation in value space. After that, we cover the main workhorse of this course, which is approximation in value space and rollout. And from a practical matter, when you are presented with a practical problem, you need to, if the methods of this course applies, you need to translate that into a mathematical problem. So we talked about problem formulation and transformation, how you can, given a practical problem, how you can formulate it as a dynamic programming problem with sequential structure that you can address using the tools you learned from this course. This includes state augmentation and terminal state problem. For example, the stochastic shortest path problem involving multi-agent architecture structure, and the POM-DP problem where some states are hidden and you need to infer. Another topic that we cover briefly is adaptive and model predictive control. These are vast subjects, and they are perfectly whole courses in their own rights, and we cannot cover everything. But those methods share conceptually similarity, and in fact, model predictive control use exactly the classical formulation model predictive control use exactly the architecture we have presented just a moment ago. Then we focused on the online play algorithm, which is the chapter 2 of the textbook. And this includes rollout algorithm for deterministic and stochastic problems, their variations, for example, fortified, simplified, constrained, model-free, and variance reduction ideas. We talked about multi-step look-ahead search for deterministic problem. This involves pruning and double rollout. In particular, double rollout, we have presented it in the context of most likely sequence selection problem. And we also talked about multi-step look-ahead for stochastic problems. And here we might need to use certainty equivalence approximation and Monte Carlo tree search. After that, we talked about multi-agent or multi-component control problems and their variations, including variations involving signaling and even problems with non-classical information pattern. And in the last lecture, we covered Bayesian optimization, whereby we transform the problem or we view the problem as a POM-DP problem, and it includes a special case sequential estimation and adaptive control, as well as where we can use rollout, and we demonstrate a case study of Wordle application using rollout. So having summarized what we have covered up until now, here's the plan for our future lectures, which is the chapter 3 of the textbook. We will cover in some depth and detail approximation in values and policies using neural networks and other architectures. We'll talk a little bit about training of approximation architectures with incremental gradient methods. And after that, we're going to talk about approximate value and policy iterations with approximation architectures, as well as aggregation methods, which is also a broad class of method and have sound theoretical guarantees. And in this core lecture, I'm going to talk about the first 2 ideas. The remaining 2 ideas will be covered in the next lecture by James. Note that we have left out a lot of ideas or topics that have been covered to a larger extent in previous offering of the courses, as well as the textbooks in 2019 and the theoretical monographs on dynamic programming. This includes a lot more theory of infinite horizon problems. You may notice that mostly in the course, we have focused on finite horizon problem, except in the context of linear quadratic problem, where we aim to illustrate this Newton's method interpretation. That one is infinite horizon, but mostly for the most part of the course, we have focused on finite horizon problem. And finite horizon problem is intuitive and easy to digest. In comparison, infinite horizon problem have a lot more theoretical difficulties, and in the artificial intelligence and reinforcement learning literature, you often see the framework that people often use is problems involving finite state and finite action and discount on the cost or reward. And given this kind of setup, that class of infinite horizon problem is quote unquote easy, in the sense that a lot of mathematical complications disappear. On the other hand, there are more challenging type of problems where when this discount factor disappear, and there might be some state that once you get to, you cannot escape. This is called absorbing state or termination state. And this type of problem have a lot of mathematical complication and involve a lot of theoretical problems need to be addressed carefully. And those things we left out. And for those of you who are interested, and you might consult to this monographs. So another subject we have left out a lot of details is stochastic training method for approximation in value space. We're going to cover in this course just a very high level overview of some main ideas of training architecture, neural networks, and so on. But there are other kind of training method, or one might view them as stochastic approximation method that include TD lambda and other TD methods for policy evaluation, for example, Q-learning. This kind of method have a lot of have imposed a lot of interesting mathematical problems that intrigued a lot of mathematicians who worked on it since the 90s. And for example, there is a elegant, also famous proof for Q-learning, which is done by professor's co-author of this NDP book, Neurodynamic Programming book, John Sisicles. And it's a lengthy proof why Q-learning works in the case where it does not involve any approximation architecture feature, but rather suppose that all the states can be enumerated as lookup tables. So there are tremendous amount of literature on those for those mathematically oriented students. And there are also specialized methods for approximation in policy space. Those are policy gradient methods and random search methods. So we have not covered the policy gradient methods, and this type of method can be viewed more generally as solving some sort of optimization problem. It may be viewed within the dynamic programming context, or it may be viewed as outside of the dynamic programming context by simply regarding it as a gigantic optimization problem. So those are things we have not covered. Now let's go back to this fundamental architecture, approximation in value space for online control selection. Recall that in the case of one-step lookahead, it involves three major approximations that we can play with. So the first is approximating this cost to go by using, so if we have access to J star, that's great, but most likely we don't. When we came across some practical problems, we use some function that we can compute called J tilde in place of J star. And there are a lot of methods we have covered, problem approximation, rollout model predict control. And this course, we're going to cover parametric approximation and neural nets. And the next one, I'm going to cover aggregation method. Another place we can approximate is this expectation. In most cases, we don't have exact formula that we can play with regarding the distribution of this WK. And some other cases is that it's way too complicated to calculate. So instead, we might want to do some simplification by using certainty equivalence, adaptive simulation, and Monte Carlo tree search, and so on. So the third one, source of approximation is this minimization optimization, whereby minimization operation, whereby in the case where their problem have multi-agent architecture or structure where UK is composed of several components, we may optimize them one after the other. And we have case study in the previous lecture that show the effectiveness of this kind of operation. Apart from one-step lookahead, there is also multi-step lookahead, whereby instead of optimizing or minimizing only the current control UK, we also optimize the subsequent L-1 stage policies. Note that there is a big difference that for the first step, we optimize UK, which is the control. And the reason is that we know precisely what our current state is, XK. But after the first stage, we don't know what the next stage is because it's stochastic. There is uncertainty involved. So we need to optimize over policies. And this makes this problem, for example, even this L is only 2, that doesn't mean the solving this problem is twice as hard as solving this one. Actually, most often it's way more challenging. And that makes certainty equivalence type of idea even more relevant in this context. Now let's cover the parametric approximation architecture used for offline training. There are two types of offline approximation in reinforcement learning. One is cost function approximation in finite and infinite horizon problems. So we may approximate the optimal cost function JK star or J star. So JK star means in the finite horizon context. So for different stage, we need to have a different cost function approximation. And J star is infinite horizon context, since different stage does not change the optimal cost. So we have one cost function approximation. And we may also approximate the optimal Q function, which is Q star K and Q star. Another type of object we may approximate is cost function of a policy, which is J pi or J mu of certain policy, or their respective Q function. In some context of finite horizon problem, you may transform it to an infinite horizon problem by aggregating the state with stage so that you have one parametric approximation to cover all cost function approximations. So this is what happened in AlphaGo and AlphaZero kind of context. Another type of object we would like to approximate is policy approximation in finite and infinite horizon problems, whereby we would like to approximate either the optimal policy, mu k star or mu star, or a given policy, mu k or mu. So if we have access to the optimal cost function or the optimal policy, of course, that is a better object to approximate, but most often we don't have access to that. So we need to turn to certain cost function or certain policy to approximate. And in particular, we will focus on parametric approximation architectures, whereby the either the cost function approximation or approximation policy approximation is parametrized by some parameter R, and in the context of neural network, this would be referred to as weights. And so we don't consider the modification of the architecture or the modification of the approximator, for example, how many layers and so on. We suppose those are given, and our goal is to optimize or find the parameter that fit the best the data we are given. And an example is the neural network where R is a set of weights, and we will give a specific example shortly. So, any questions to this point? Yes, please.
I always have this question for the finite horizon problem.
Yeah.
Where J cost function, you have like a or state step number.
Yeah.
Does the cost function depend on the step number, or can we have like a universal cost function for finite horizon problem, just as?
So, for example, in many of these finite horizon problems, the state that you occur in different stage are different. Let's assume that we have a finite horizon problem. At x0, you can only have state 1, and at x1, the first stage, you have state 1 and 2, and then 3 and 4 in the third stage, and so on. And if the states are distinct at different stage, then it doesn't hurt for you to use one parametric architecture to approximate the entire thing, because the same state cannot appear in different stages. So given the state, you know precisely which stage you are at. Then it's fine to use the same architecture to approximate the whole thing.
Is it saying that, let's say we already use like a neural network to approximate the cost?
Yeah.
Right? Like under what circumstances you need to use, let's say, more than one neural network in your example?
For cost function.
Yeah.
So suppose you are solving a shortest path problem, and you formulate this shortest path problem as a finite horizon problem. Okay, technically, given a shortest path problem, it's more appropriate to formulate it as an infinite horizon problem. But for the sake of this example, let's just say it's formulated as a finite horizon problem. Suppose there are 5 nodes in this graph. You want to compute the shortest path to certain node. And you know the longest distance, the shortest distance can involve at most 5 nodes, right? Then the capital N you choose is 5. We formulated this as a finite horizon problem. Then this node 1 can appear in first stage, also in the second stage, and the third stage, and fourth stage, and fifth stage. You don't really know. Suppose you supply the neural network with this node 1. How the neural network can recognize or distinguish whether or not this is first stage, second stage, or third stage, right? In this case, either you augment this node number with the stage number to make it for the same node different in different stages, or you just use different networks. And this is just a trivial example, but give you a hint about how to deal with this sort of things. And typically in context of games and so on, it's more appropriate to formulate as a shortest path type of problem, which make it infinite horizon. So you can use one architecture to approximate. But in the case where you have a finite horizon and the same state appear in different stages, and you have no way to distinguish which stage it is, then you need to augment it with the stage, or use different separate neural networks. Okay. Yes. Yeah, by horizon, I'm referring to finite horizon. I'm referring to there are finite number of stages, and after reaching that stage, everything is completed or over, and so on. Infinite number of state possibility, but stage is finite, right? Then it doesn't make any difference. I mean, if it's infinite number of states, then either if this infinite number of states, so the key is whether or not in the context of finite horizon problem, whether or not your current formulation, whether or not the same state appear in different stages, and whether or not your neural network can distinguish the same state in different stages. And if it can distinguish, I mean, technically it cannot, because the same thing you present, okay, x equal to 5, you present to the same neural network, it's going to output exactly the same thing. So you either need different neural network, or you need augment, explicitly tell the parametric approximator that, okay, this appear in different stages. Okay. All right. So let me give you a practical illustration of parametric approximation when we would like to approximate a target cost function. Suppose this is some target cost function we would like to approximate. And the first step is we collect a lot of training data. This data are state and cost pairs, where Q can be a large number. And we design this approximation architecture. And once this architecture is fixed, we would like to find this parameter R such that the function defined by this architecture and this parameter is close enough to this target function that we would like to approximate. So this process is called training. The process of finding this parameter R is referred to as training, and can be done with specialized optimization software such as gradient line method or other least square methods, and we're going to cover some basics of them. And note that each of those steps can be time consuming. For example, the process of collecting training data and the process of training this R. And we'll give you a flavor how those can be done. Unlike the case where we approximate the cost function, when we would like to approximate the policy, especially when the number of possible control is finite, things are a little bit different. So if the control have continuous or real valued components, the training is similar to the cost function case. On the other hand, if the control comes from a finite control set from U1 to UM, an alternative approach is possible and is also commonly used. That is, we view a policy mu as a classifier. It is a function that maps X, the state, to a category, mu of X. And if we look at this schematic illustration, given that we have a target policy we would like to approximate, either it's some given policy or the optimal policy we computed for a limited number of states, we collect a lot of training data, which is the XS and mu X over S pair. And this classifier, the parametric policy approximation, essentially is to assign the state X to a class, which is one of those M different classes by once we fix this parameter R. So after the training, we have the freedom to either use just sample from this. So in some case, the trained classifier can be randomized, and then we may simply use this randomized policy. In other cases, so basically the output most often is a control probabilities, that is a distribution over the control space. And in most cases, we would like to just take the max operation and use the control that corresponds to the biggest probability. So some classifiers have the randomized policy, as we mentioned in the last lecture, this GPT application. And the output of this classifier would be the control probabilities. Note that there are extensive open source software available that you can use for training such classifiers. And the randomized policy have the continuous components. This helps algorithmically. So suppose that we have M different distinct control components, then the randomized policy would be a probability distribution, which is a continuous number defined over this M dimension object. And this helps the training process. Recall that in the last lecture, we talked about rollout application to GPT, whereby we view GPT as a Markov chain that define the transition probability between different states. But it's clear from that course, for a given GPT, it can also be viewed as a policy. So if you have some problem where the state is well-defined and the control is also well-defined, you may use a transformer, train the transformer, then the output of that transformer would be the distribution over its control space, which in this context would be its vocabulary. And in this case, the GPT can be viewed as a classifier with the output being the control probabilities. And quite often in this context, randomized policy are often used. So as we see in the previous lecture, it outputs the distribution over the entire vocabulary, but you may modify the output by imposing additional constraints. And that has been done in practice to suppress the repetition of the text generated in the previous string and so on. Now let's go back to the cost function approximation. So cost function parametric approximation have, we start with a class of function, J tilde, that depends on X and on a vector R, the M-dimensional vector, which are tunable scalar parameters. So each one of them is a tunable scalar parameter. And we adjust R to change J tilde so that it matches the training data from the target function. Again, we leave aside how we get those training data and so on. those can be quite complicated, and there are some subtleties or techniques involving what is the good training data to collect and what is not, and it involves this fundamental trade-off for exploration, exploitation, and so on. But we just focus on how this training process and architecture is modified. So the training algorithm is the algorithm that chooses R. Typically, given that we have obtained the pair of state and cost function, and this training process would be a regression type of process. Depending on the architecture type, we call the architecture linear or nonlinear. So if it's linear in R, then we call it linear. If the cost function depends nonlinearly in R, then it's nonlinear. If there are explicit features that we have relied upon to build our cost function, then it's called feature-based. More specifically, if the cost function approximation, J tilde of X, is dependent on X through indirectly through the use some feature vector, then it's called feature-based. So where J hat is some other function. And the intuitive idea here is if the phi of X captures the most dominant nonlinearities, hopefully this J hat can be relatively simple function with respect to phi of X. In particular, a linear feature-based architecture looks like this. Given a set of feature, set M of feature, phi of L, the cost function looks like this, which is the linear sum of the features where the parameter RL is the parameter we aim to train, and can be viewed as inner product of two vectors R and phi of X, where RL and phi L are the else product component of those two vectors respectively. So when applying this linear feature-based architecture, given a state, we first construct its features by going through this feature extraction mapping. After that, we obtain this feature, phi of X, and this phi of X should capture some key characteristics of the state, and then we linearly combine those feature components to get a linear cost approximation R prime phi of X. A simple example of a linear feature-based architecture is this piecewise constant approximation, whereby we partition the state space. In this particular example, the state space is a line, is one-dimensional. We partition the state space into subsets S1 to Sm, and the else feature is defined by the membership in the else set SL. So it is defined essentially by this indicator function that if X belongs to this subset, then this feature is 1. And if it does not belong to this set, then this feature equal to 0. Recall that partition means that we divide the state space into different parts that collectively exhaust all the state space, but there is no overlapping between each other. So each state can only belong to one and only one, must belong to one and only one subset. And given this feature, then its corresponding linear feature-based cost function approximation would look like this, whereby we combine the weighted sum of those linear features for all the states that belong to this subset SL, then its cost is determined by the else component of the parameter. So it's piecewise constant and kind of staircase. So this sort of architecture is fairly powerful in theory and can approximate a lot of complicated cost function. But the problem is when the cost function is complicated, you need a lot of carefully designed subset to partition the state space. And this example is one-dimensional, and it can be, once they get into high-dimension state space, it would be way more complicated. Another thing you, yes, please. Sorry? No, this is the cost function approximation. It's state. So, well, not necessarily true. For example, let's say I'm talking only about integers on this line, and integers up to some number, let's say 50. Then you can still partition them into distinct disjoint groups, right? Okay, we have not talked about open and close and so on, but the main point is it just have to be a partition of the state space that each state belong to one and only one subset, and that's enough. Okay. So one additional property you may notice is that if I change the value of a particular component, RL, let's say this number, if I change this number, then the cost function of all the states all the other states does not change, except the states that belong to this SL subset. So this is kind of the locality of this sort of cost function approximation. And the one we're going to see next is the opposite, whereby you change any component of the weight, it's going to affect the entire cost function for all the states. So another type which is commonly used is generic polynomial architecture. And if we focus on a quadratic polynomial approximation, given that we have an X with n different components, its features can be viewed as those combinations where it includes a constant shift and also individual components and products of two components. Then a linear feature-based approximation architecture of this features would be one weight associated with this constant, and each weight is associated with one individual components and one weight for each, one parameter for each combination of product. And the parameter vector R has components R0, Ri, and Rij. Generally, we don't need to stop at the quadratic terms, and we can have higher order polynomials in components x1 until xm. And an even more general architecture is in place of x of I, we may have, instead of directly use x1 till xn, we may construct feature vectors phi 1, phi 2 until phi m, and we use polynomial terms of those phi's in place of xi and xj, and typically this architecture should be more powerful, but the choice of those features are also important. Let's briefly comment some features used in some case studies. For example, the application of chess, the feature extraction module typically would take the material balance, mobility of the mobility and the safety of king, for example, and those features typically would be recognized as important for a chess player. And for the application of Tetris, a set of important features. Okay, so I suppose all of you know Tetris. And briefly, it's you are given a board, and you would like to fill each row of the board with those blocks. And once a line is filled, you get 1 score, and that row is removed. And the goal is to maximize your score up to certain stages or indefinitely. So in this context, the typical set of features that are important is, so once if there's any row that reach the ceiling of the board, then the game is terminated and is finished. So the typical set of feature that is important includes the height of each row and the relative height of each row. For example, the adjacent difference between different rows, between adjacent rows. And typically we would like the height of the rows to be more or less balanced. We do not like the case where a certain part of the row are very high and a certain part are very low. So those are the typical features that indicate how well the situation is. And other features includes the maximum height of the different rows, as well as the number of holes. Because if there's a hole, then you don't have access to that particular position and you cannot remove that one. So those set of features are widely used, and since 90s, the points of method that obtained using reinforcement learning method or related method have starting from hundreds and at current stage can score billions of points. So there has been tremendous development in this direction. Okay. We talked about partition of the state space, and a straightforward way to partition the state space as illustrated in the previous example is just cut the state space into pieces in that scalar example with different intervals and so on. But another simple method to construct relatively complex approximation architecture is to partition the state space into several subsets and construct separate cost function approximation in each subset. So in this case, for each and individual subset, we construct a separate cost function. And an important issue, practical issue to deal with is that once you partition the state space into different parts and use different cost function to approximate different parts, the states that are close to the boundary of the partition need to be coordinated in the sense that when the states are shifting between or transitioning between different parts of the states. If, let's say, they are geographically close states, and if different, but they are belong to different partition subsets, and if they are shifting from one part to the other, this kind of shifting issue need to be dealt with, so that, for example, for states on the boundary or close to boundary, there are you need to pay special attention. And it is often a good idea to use feature to generate partition. Again, as I mentioned a moment ago, that in the previous example, we simply partition the state space into different parts, which are regular in the state space. But a different idea is that we use some feature and we look at states through feature extraction, and we do regular partition of the feature space, and then we map it back to the state space, so that, for example, states belong to the same subset of the feature space should be grouped together in original state space. And intuitively, we would like to group together states with similar costs. And as you may recall, feature typically capture the majority characteristics of the nonlinearity of the cost function. So ideally, states close in the feature space should have similar cost function. We hypothesize that states with similar features should have similar cost. And the manifestation of this idea arises in feature-based aggregation, which we're going to talk about in the next lecture. Okay, so up until this point, we have talked about the features that we manually construct in those two case studies, chess and Tetris. But a more popular architecture nowadays that construct a feature for ourselves is neural network. It is an architecture that works with no knowledge of features. Of course, it may still help do some state encoding, that is, given the state that defines the problem, we may use some architecture which we refer to as state encoding to construct some states, which is a mapping from X to Y. But regardless of the presence of this layer, a single layer neural network is composed of a linear layer where this Y of X is multiplied with some matrix A and then add a bias term B. And each and every component of this linear layer output would go through a nonlinear layer, and with their values to be called phi of X and V. And then those features are combined by a linear weighting parameter R. So conceptually, this part can be viewed as the feature that we constructed in the previous examples. Let's briefly talk about the training of the architectures. Typically, in the context of approximating the cost function or approximating a policy with continuous component, it can be viewed as least square regression problems, where we collect a set of state and cost training pairs, XS and beta of S, where the number of samples can be large, and beta of S equal to the target cost function evaluated at XS plus some noise term. And the weight R is determined by solving the least square problem, whereby we would like to, we sum up the quadratic difference between J tilde and beta S summed over all the samples and minimize the weight or parameter R. Sometimes a quadratic or regularization term, beta times the norm of R, is added to the least square objective to facilitate this minimization. And there are numerical reasons I'm gonna touch upon in a moment. But another important reason is that it helps to avoid the issue of overfitting. On the other hand, nowadays, overfitting in the context of deep neural network turns out to be a good thing. So, I mean, things change over time. I mean, back in the days, overfitting is a horrible thing, but now it become a blessing. All right, so the training of linear feature-based architecture actually is quote unquote the easy case because it can be done exactly, by which I mean we have formula to compute it. So if this J tilde equals to R prime 5x, where 5x is the m-dimensional feature vector, the training problem involves quadratic minimization and can be solved in closed form. And this closed form formula is given by this equation, where it involves this inverse of matrix and then multiply this vector. Even though it looks reasonably innocent, but it can be quite challenging because when the m is large, so suppose that, note that this 5x is a vector, m-dimensional vector, column vector, and 5 prime is m-dimensional row vector, then this is the m by m dimension matrix. So you compute this matrix, you add q different matrix together, and you compute the inverse of it. And any one of those operations, especially inverse, can be quite challenging if the m is large and q is large, and there can be numerical issues arise if this matrix is near singular, then computing the inverse can be quite challenging. And in this context, adding this regularization term can be helpful because with this regularization term, there are going to be one additional term added in this brackets to make the inverse operates more easily. So, but practically, it requires a lot of computation for large M and data set. Therefore, it may not be best. So more generally, we have a nonlinear architecture, and how can we exploit the structure of the training problem of this minimizing a large number of quadratic terms? The key characteristics of the training problem, it's possibly non-convex with many local minima, and can be horribly complicated graph of the cost function, especially true when the neural network is used. There are many terms in the least square sum where Q is very large. This makes standard gradient and Newton-like method essentially inapplicable. As a result, incremental iterative methods that operate on single term at each iteration have worked well enough for a lot of problems. Okay, let's take a quick break here. And we get back in 10 minutes, 49 or 50. All right, let's start with next topic, which is incremental optimization of sum of differentiable functions. And the training problem, training architecture we touched upon a moment ago would be a special case of the more general problem addressed here, where we would like to talk about incremental gradient methods invented in the 80s, and but it has been analyzed and extended in the 90s, and is still important research topic to the present. So we're going to focus on this generic sum of term optimization problem, whereby we would like to minimize f of y, which is the sum of component functions fi of y, where each fi is a differentiable scalar function of the n-dimensional vector y. This is a parameter vector in the context of parametric training we talked about. So more specifically, if we consider the problem of neural network training, then each component would correspond to one sample data point with the state. Let's say if it's cost function approximation, then every component would correspond to one state and cost pair. And the ordinary gradient method is generate a sequence of parameter n-dimensional vector y from yk plus 1, generate k plus 1 from yk according to this formula, which is changing yk to with this term, which is the opposite of gradient evaluated at y of k, fyk, scaled by gamma k. And given the function f of y, which is the sum of the components, then this gradient would be the sum of the gradients of individual components, where this gamma k is some scalar bigger than 0. It's called a step size parameter. This method is origin is attributed to this French mathematician called Cauchy from 1850s. So it's an old method. And there are extensive theory which show the validity of this method. In some ideal scenario, we can the obtained y, the limit of the sequence would end up being the one we are hoping for. But as we mentioned a moment ago, in the context of training, this m can be enormous, and computing this sum is very expensive. And the incremental gradient counterpart of this ordinary gradient method is simply choose some ik, index ik, and iterate according to this formula and compare it against this one. This essentially means that instead of summing over all component, we just choose one index and compute the component functions gradient and use that in place of this one. And this seems to be a remarkable saving of computation, given that m can be huge. But one might ask, why does this work? Well, actually, intuitively, it's there is a elegant explanation. Suppose that this function f of y is the sum of square, which is ci times y minus bi squared. And we would like to compute y such that this function is minimized. And again, if we go back to the training cost function type of context, we may consider this function actually is we have some linear function, cy, and we would like to compute y, where y is actually the parameter. We would like to compute y such that this function y times c approximates some function b well. And then we collect state and cost pair, where c would represent the state and b would represent the cost. So essentially, this is the difference between the linear cost approximation we have, and this is the cost from the training data we have, and we would like to minimize the sum over all the sample data. And compare the ordinary and the incremental gradient method in those two, two different cases. Start with the place where, let's say, where y is far away from this middle portion, which is referred to as region confusion. And the part that far away from this region would be referred to as far out region. One can show for this example, the true optimal lies in somewhere in the middle, defined by this interval that is the minimum of the optimal for individual components. Suppose, for example, let's consider C1y minus B1 squared. We can compute its minimum point and its optimal by simple calculus. And the minimum among all those y's and the maximum of all those y's defines an interval. One can show that the true optimal actually lie in this closed interval. And the region beyond this region is called, beyond this closed interval is called far out region. And this interval is called region of confusion. So when far from convergence, which is in somewhere here, the far out region, the incremental gradient is as fast as ordinary gradient with 1 over m amount of work. How so? So let's suppose the current yk is somewhere here. Then regardless of the ik you choose to evaluate the gradient, it all point to the same direction. That, okay, you need to move to the left in order to have the cost reduced. But of course, on contrary to ordinary gradient method, you only compute the gradient of one component, which is a lot of computational saving. On the other hand, when close to convergent, that is, if it's somewhere here, the current yk, then the direction for the update depends on the component you choose. If you choose this particular component, it's gonna tell you to move to the right. Whereas if you choose this component, it's gonna tell you to move to the left. So once it get into this region, it's gonna move left and right and without knowing what is the right direction to go. So, but theoretically, there are ways to avoid it. And that is, you can design the step size to be diminishing so that it can converge properly. So there are also variants of incremental method, which is called incremental aggregating method, that should accelerate the convergence process. Evaluates the gradient of, so the incremental gradient method evaluate the gradient of single term at each iteration, but it used previously calculated gradients as if they are up to date. So but that means you need to have a memory to keep track of the previous round of calculated gradients, and you sum them up. And it have theoretical and empirical support and often preferable. So in the context of training neural network, you hear a lot about stochastic gradient method, also called stochastic gradient descent, or SGD. They apply to problems of minimizing a function, which is the expectation of some component function, where W is a random variable. And in this context, this algorithm has this form where starting from YK, it computes the gradient of F corresponding to a particular random variable value. Is a sample of the, so WK is a sample of the random variable, and the gradient of F with respect to Y denoted the gradient F, okay, gradient of F with respect to Y is the symbol. And the incremental gradient method with random index selection is the same as SGD. If we select the random index according to uniform distribution or uniformly, then it convert the sum of component function to an expected value where I is the random. So the I would be this W with uniform distribution. So there are some practical issues for implementing incremental method. One is to how to select the step size, gamma k, as we alerted to a moment ago that when it's closing to the region of confusion, one might like to have diminishing step size to ensure convergence. So the typical choice would look like this, where gamma is some scalar, and with the increase of the iteration, the step size diminishing. Another issue is how to deal, if at all, with the region of confusion issue. That is, once the YK enters the region of confusion, we would like to start to use the diminishing step size in order to convert to the right value. And when it's outside the region of confusion, there's no real need to use the diminishing step size. So detecting the region of confusion and start to reduce the step size, this is another issue you need to deal with. And another one is how to select the order of terms to iterate. Recall that in the incremental gradient, we select at each state, at each step, IK, a component and compute its gradient. Then the question is how to select that IK. And one way is to order the component in a certain way and just circle through those components. And the other way is to do random selection, and at each step, select randomly according to a uniform distribution. Whatever the selection approach is, the important thing here is you need to make sure the selection process corresponds to the uniform distribution of all the components. For example, if you select, let's take the extreme case. Every time you select the minimum index, okay, you always stick to the same component all the time, and you put huge bias on this data, and that is not ideal. So the important thing is to make sure that you cover and you give equal attention to all the components. And there are other methods called such as diagonal scaling. Essentially, this means a different step size for each component of Y. Recall that Y is, in the context of training neural network, for example, each component of Y is one particular weight. So it's very high dimension, and you may use different step size for different components. Alternative methods includes incremental Newton method, extended Kalman filter, and those discussed both in the course textbook as well as references. Okay, any questions here?
Can you reiterate how you, so there are previous slides by where you do CI and BI and
oh, okay, this one. Yeah.
How do you choose CI and BI and
so those are parameters, right? So this problem is a sum of components, and we would like to minimize. And fi would be the function that ci times y minus bi squared. So this is each I corresponds to one component, and ci and bi are parameters, and we would like to find y that minimize this entire function. And if I use the metaphor of training some cost function approximation, then that cost function approximation is linear in this case. And the state would be the C. And the weight or the parameter would be this Y. And this BI would be this cost function we get from the training data. So this is the X, this is the J, basically.
And Y here is vector or
Y
scalar?
in this particular case it's a scalar, but this metaphor carry through to high dimension examples as well. Yeah. Okay, let's get to some basics of neural network. As I alluded to, that neural nets are architecture that automatically construct features. And here is an example of neural network with a single layer. And if we connect neural network with the training algorithm that we have discussed, then given a set of state and cost training pairs, X, S, and beta S, where each S corresponds to one sample, training sample, the parameters of this particular neural network obtained by can be optimized or learned by solving this training problem, where for each sample, we try to minimize the square of the difference between the output of this neural network. Again, recall that for starting from X, we go through state encoding process to have Y of X, and then go through this linear layer, A times Y of X plus B, and then each component goes through this nonlinearity layer, and then they are combined linearly by this vector R to have a single number that approximates cost function value evaluated at this state XS. And we take the square of this term and try to minimize the sum of all the terms. So for this problem, incremental gradient is typically used for training. And what is ideal is that theoretically, there is a universal approximation property that states neural network, even with one single layer, can approximate any target function of arbitrarily well with sufficiently large neural network size. So as long as the number of nonlinearity in this one single layer is large enough, whatever continuous function you have as a target, this neural network can approximate. But the question, the practical question here is how many those nonlinear layers, nonlinear units exist in this nonlinear layer. And sadly, this is where the correct theory makes things worse, because when this universal approximation theory is out and everyone start to work only with shallow neural networks, and people feel it seems ridiculous or really not so smart to still work with neural networks with more than a few layers, given the presence of the theory. But the theory intuitive, but it's misleading in the sense that, okay, perhaps it's not fair to say misleading, but it never answered the question how many the nonlinear units are needed in order to approximate certain function. And as it turned out, the opposite is having deeper neural network is a better way. So before we go to deeper neural network, let's look at what are the typical nonlinear units that are used. And the two on the top are rectified linear units, RuLu, and it's simply 0 for number that is smaller than 0, and then a linear line for whatever number that is bigger than 0. But as you recall that I have mentioned all the time that the training problem and so on, they are dealing with differentiable functions. So people have used a smoothed version of this function using this form so that we have a function that is differentiable and the efficient training algorithm can be applied. And those are more modern activation functions that is used. And however, the present GPT applications and so on, they use a slightly modified version of this smoothed version of rectified function. Note that here, the smoothed part is above 0, but the GPT-2 and rumor have it 3.5 and so on use GALU, where the smooth part is below 0. So this is a slight difference. And there are empirical studies that show why this is chosen and so on. In the old days, the sigmoid function, sigmoid units are more preferred, and those are hyperbolic tangent function, where not only value below 0 is saturated, but beyond certain range, it's gonna also saturate around 1. So the logistic function looks similar in shape. Now, as I mentioned a moment ago, that this universal approximation theory tells us all you need to do is to have one nonlinear layer and have the number of nonlinearity large enough. You can approximate whatever continuous function of your desire. And but in recent years, we all know that the tremendous glory brought to neural network is by their deep counterparts, whereby starting with state encoding, it goes through a linear layer and nonlinear layer, and then this linear and nonlinear layer is repeated after a tremendous number before we finally settle with some linear weighting function. And the practice has shown this form is way more powerful, and extensive research has gone into explaining why they are more effective than the shallow neural nets for some problems. And one key observation from some recent research suggests that over parametrization is the main reason. That is, you have more parameters than data. Generally, the ratio between the number of parameters or the weights over the number of data points affects the quality of trained architecture. And this number we denote as R. And we call it over-parameterized if R is bigger than 1. If R is approximately equal than 1, the architecture tends to fit very well with the training data. And this caused the problem of overfitting, but do poorly at state depth outside of the data set. This is a horrible thing to do in old days. But now, with R that is much larger than 1, in practice, it shows that the overfitting problem actually is overcome. So here is an interesting exercise for you to try. Is in some current state-of-the-art open source language model, they publish a number of parameters, the number of weights, as well as the data set they have used. Not precisely the data set, but the size of data they used. So it suffices for you to have an estimate how many data points they have used for training those large language models and GPTs and so on. And given those information, as well as some other parameters like the number of n-gram, the number of n, in that context is called the context window and so on, you can actually compute the ratio between the number of parameters and the number of data points. So if any of you interested, you can try, for example, this language model from Llama. They have published the training parameter, the training data points, as well as the number of data, as well as the number of weights, and you can compute their R to see whether or not it's over-parameterized. Anyways, apart from the attention mechanism that we discussed before that apparently bring a deep neural network to new height, there has been main important milestone techniques or designs that enable the use of deep neural network. And we're going to cover briefly, talk about 2 key ideas, and one is residual connections, and the other is layered normalization. So recall in the previous figure, after state encoding and so on, there is a linear layer, and then there is a nonlinear layer. It may be repeated, and the output here may be weighted and summed together act as output. But around 10 years ago, researchers have found that with the number of layers increase, then it seems the performance increase saturated and even perform worse than shallow neural network or their shallower counterparts. Then why might I ask how so? Why it is saturated? And an interesting idea, a very insightful idea that come about is how one can design architecture so that it is guaranteed the deeper the network is, it is guaranteed to at least not perform worse than their shallower counterparts. So they came up with this basic building block architecture. We're starting from a linear layer and then goes through a nonlinear layer and then another linear layer. And what is interesting is that all the input layer is then added together with the output of this last linear layer. And this is used as output of this building block. And this building block can be repeated, connected one after the other to construct a deeper neural network. And what is nice about this building block is that when the weights are selected such that y tilde here are 0, then this building block is essentially skipped, which means we have constructive ways to design a shallow network out of a deep neural network using this building block. So a deep neural network can reproduce the output of its shallower counterpart by skipping its additional layers. And this turned out to, or intuitively, this implies adding more blocks is likely to improve the performance, and turn out to be the truth, and is one of the cornerstone of the current state of all the successful neural network application we know. Another idea is called layer normalization, which facilitates training. So after the linear layer, the output goes through the nonlinear layer, and we have phi 1 until phi m. But instead of directly going to another linear layer, there is a linear layer normalization block that take as input all those phi's and then output phi's of the same dimension. And it involved this calculation, which compute the empirical means of all the phi's, as well as the empirical variance of all those phi's, and then normalize those phi I using this formula, basically shift all the phi's around 0, and then divide it by the variance where epsilon is a small fixed number, so that the phi hat are, on average, are around 0. There can be some scaling, additional scaling or bias term added for all those phi hat. So why one would like to do this? Intuitively, one can think that after this layer normalization, phi hat would be the empirical distribution would approximate this standard normal distribution. And recall all the trainings, all we have done is manipulating the gradients and so on. And if the number are far away from 0, then the gradient is going to be around 0 as well. And one would like all those numbers to be concentrated around 0 so that the gradient can be computed, the meaningful gradient can be computed. So that's all the content for this course. And in the next lecture, we're going to cover value and policy iteration using neural network and introduce the aggregation method.